So we'll get going. It is 1:02 on Saturday, April the 10th. Welcome, everyone. Hopefully it's sunny where you are, because I know we have members from near and far. So welcome. We're hoping to address a whole bunch of topics today that will hopefully keep everyone interested in what's happening. And as well, excuse me, just want to remind people that this is being recorded. It will be available in a couple of days on our RASC Halifax Center YouTube site. So if you have to deke out for whatever reason, or you want to watch part of this again, you can in a couple of days on our RASC YouTube site. If you have any questions, please put them onto the chat during any of the presentations, that is. And we will certainly ask them at the end of the presentations, unless the presenter states right up front that they don't mind being interrupted for questions. You can unmute yourself and ask. If you haven't already, and I think I've made sure that everyone has muted or is muted, but just make sure you are muted so your sounds from your computer don't interrupt the rest of the meeting. So for guests who've never joined us before, welcome. And you can become a member if you aren't already. There are several perks to becoming a member, such as this wonderful production on the Observer's Handbook. And our associate member from Regina Center, James Edgar, is the editor of this. Not to mention, there are 9 of our center members who are also contributors to this wonderful production. So it's a great reference resource. And you can see that I've already got mine marked in several places that I want to look at on a frequent basis. Also, as a member, you will also get your own personal copy of Explore the Universe Guide, which is an explanatory piece on all the various pieces that you need to know about Explore the Universe. And if you want to, anyone can do this. You do not have to be a member for this particular program. You can order the book, and it has the lists as well as the observing sheets that you can fill in as you explore the universe. And I'll tell you more about the program later on in the meeting. You also get a subscription to RASC's news magazine, Sky News. All sorts of neat and wonderful articles in there, Canadian related, a lot of them. And certainly in the journal, you get a subscription to the Journal of the Royal Astronomical Society of Canada that comes in every second month, basically. There's some really neat articles in here. In this issue, there's a Blake Nancaro's article on the Double Star program that Dave Chapman will talk to and Melody Hamilton will talk to later in the meeting, as well as David Levy, his article. He's got an article on the Christmas star in Orion. And if those of you who attended the meeting during the conjunction of Jupiter and Saturn, Paul Heath did his poem about the Christmas star. And as well, Randall Rosenfeld also has a really neat historical perspective on colonialism and astronomy in Canada that you might want to have a read. So those are the benefits of joining from the national perspective, but certainly from our perspective, you also get your subscription to Nova Notes. Our 2 editors, Lisa Fanning and John McPhee, have produced this their first edition, and we'll tell you more about how you can contribute to Nova Notes later on in the presentation. So there are lots of neat and wonderful things. Also, as a Halifax Center member, you also have access to our library and to our observatory. But the most important part of all of this is the amazing people that you have access to help you go through all the programs and through any questions regarding equipment or observing or any aspect of astronomy. That, to me, was the biggest piece, is that how willing people are willing to help you, mentor you as you go through and learn more about what aspect you're interested in. Also want to bring your attention to the fact that we still have some RASC calendars here that if anyone is interested at this late date in purchasing one, they can. And you can access them by sending $25 to our treasurer at halifax.rasc.ca. His email address is on our Contact Us page. You just have to send it to him and with your name and address, and they will certainly make sure that you get your copy. As well, as you know, we have had a fundraising drive over the past several months to fundraise towards our upgrades at our observatory. Those of you who haven't, who would like to make a donation, can still do so by contacting our treasurer at halifax.rasc.ca. The details are there on our website if you have any further questions regarding that. But please note, unfortunately, because we are not a charitable center, we cannot issue tax receipts. That's one of our downsides. On a positive note, happy birthday to anyone who's been celebrating a birthday over the past month and will be doing so over the coming month. Congratulations on another successful circumnavigation of the sun, and may there be many more. And we'll wish happy birthday to those of you who are with us again on May 1 at our next meeting. And at this point, I'm going to share my screen for a couple of slides. So welcome everyone to Halifax Center. Welcome again. Just a note that RASC, as well as RASC Halifax Center, believes in and practices inclusivity and diversity. All are welcomed regardless of age, disability, gender reassignment, marriage and civil partnership, pregnancy and maternity, race, ethnic origin, color, nationality, national origin, religion or beliefs, or sex and sexual orientation. And we are opposed to all forms of unlawful, unfair discrimination. For the first time, we will be making an Indigenous land acknowledgement, and this will continue in all of our meetings. RASC Halifax Center would like to begin by acknowledging that we are in Mi'kma'ki, the ancestral and unceded territory of the Mi'kmaq people. This territory is covered by the treaties of peace and friendship with Mi'kmaq and Maliseet peoples, first signed with the British Crown in 1725. The treaties did not deal with surrender of lands and resources, but in fact recognized Mi'kmaq and Maliseet title and established the rules for what was to be an ongoing relationship between nations. Our agenda for today is really quite simple. Following my little blurb, we will introduce our first guest speaker, Adam Gonzalez, who will be addressing high velocity outflows in active galactic nuclei, his PhD thesis. So we're really looking forward to Adam's presentation on that. That'll be followed by a presentation with Dave Chapman and Melody Hamilton regarding the RASC Double Star Observing Program that I mentioned is described in one of our journals. One of the things that we've implemented new for the first time is a members question period, and I'll describe more about what that's about when we get to that part in the agenda. That will be followed by Dave Chapman's What's Up in the April Skies. He'll tell us what neat, wonderful things to look for. I will then give a presentation on news from the board, and then at that point, the recording will cease, and members and guests are invited to join us for the following hour for an astro chat. Very informal, talk about anything and everything. So you are welcome to do that. So please join us afterwards. And stop the screen share at this point. So at this point, the next thing on our agenda was our guest speaker, Adam Gonzalez. I know he's here. Welcome, Adam. We're really thrilled to have you join us today, and thank you for volunteering. Adam is in his final year of his PhD thesis at St. Mary's University, working under the guidance of Dr. Luigi Gallo, who we heard speak last month. Adam completed his Bachelor of Science in 2015 at McMaster University before moving to Halifax to attend SMU, where he completed his master's in 2017. And I'll let him describe that aspect of his work during his self-introduction. And his PhD work that he's completed has focused on the subject matter of today's presentation, which is high velocity outflows in active galactic nuclei. So to that end, Adam, take it away and welcome.
Thank you very much for the introduction, Judy, and good afternoon, everybody. I will start by sharing my screen here. Hopefully everybody can hear me all right. Let's see this screen here and go up here. Oops, click this. So you should all see my slide, my title slide here, high velocity outflows in active galactic nuclei. So yes, once again, thank you very much for that introduction. I'll try and focus on this camera since I've got two screens set up here and camera's only on one of them. So yes, thank you very much. And today I will highlight to you some of the general topics that I've been looking into over the course of my PhD at St. Mary's University. So I'm not going to get into like any super technical details or anything like that. We'll just try and cover the main interesting concepts, at least what I think so, and hopefully I can convince you all that they're also quite interesting. And so to begin, we will start with this image here on the left, taken by the Hubble Space Telescope. And some of you may be quick to recognize that this image contains many, many stars. And the stars are generally easily recognizable by the lens flaring crosshairs pattern that they produce in optical images. And this is due to the fact that they are very bright, they are nearby, and they are point-like in nature. And so if I were to show you this image now on the right-hand side, also taken by the Hubble Space Telescope, you may draw some similarities between the two images. Now, sure, the one on the right doesn't contain as many of these point-like sources and seems to be of a somewhat lower resolution if you look carefully. But what I want to point out is mostly that at first glance, they look quite similar. However, I want to stress some key fundamental differences. The first being that the object on the right is approximately 749 million parsecs away. And if parsecs don't mean anything to you, just for reference, Andromeda is approximately 765,000 parsecs away. So by comparison, this is about 1,000 times further away than the Andromeda galaxy from us, which is our nearest neighbor. And what's further interesting is that this object, by comparison, is 200 times brighter than the Andromeda galaxy. And Andromeda contains about 1 trillion stars. And so something very, very far away that is apparently point-like in nature is exceptionally brighter than an entire galaxy. So what on earth is happening here? One of the ways that we can try and figure this out is if we take another look with the Hubble Space Telescope. So the image on the left is similar to the one that I showed you in the previous slide. And Hubble has a coronagraph, which essentially allows for the blockage of a small region of space. In this case, we're going to focus in on the white square of the left image, and we're going to block out the central-most point of that very bright object. And what's immediately revealed is this greenish yellow fuzzy cloud. And what this is a very distant, far away galaxy. As I mentioned, it's millions of parsecs away from us, many times further than Andromeda. And so now the question becomes, okay, we blocked out whatever's happening at the center of this very distant galaxy, but what is going on there? And so the answer to that is this is what we call an active galactic nucleus, or as I'll refer to it from here on out, an AGN. And so what is an AGN? Well, this is how an AGN works. This is the central engine of these objects. And so what we're looking at here, just very simply, is a supermassive black hole at the center of this distant galaxy. And there's very strong evidence that suggests that every single massive galaxy in our universe contains one of these supermassive black holes. And what does supermassive entail? Well, this is something that's 1 million to 1 billion times the mass of our own sun. And some of you that may be interested in black holes might already know that one of the key distinguishing features of them is that they are extremely dense. In fact, the densest type of object that we know of in the universe. And so all of this 1 million times the mass of the sun is compressed into a volume that would be approximately the size of Mercury's orbit around the sun. So an absolutely extreme object, very far away from anything we deal with on a daily basis. And furthermore, the gravity from this is just tremendous. It is so enormous, in fact, that if you were on the surface of this supermassive black hole and you had a flashlight with you and you shine this flashlight out, none of that light would escape. In fact, it would form a pathway from your flashlight go a little bit distance out, and come right back down to the black hole. And so at this point, you might be wondering to yourself, okay, black hole, no light escapes, right? How can this be responsible for that extremely bright central point in that distant, faraway galaxy? Well, it's not exactly the black hole doing it, but it's the environment around the black hole that's responsible for that. And so what happens is material, gas, and dust, and other matter from the center of the galaxy hosting this black hole kind of fall towards it due to the strong gravity. And as this material falls towards the black hole, it starts to orbit it. And it bumps into other clouds, starts to get stretched out, and flattens into a disk. And we call this disk an accretion disk. And what's happening here is that matter is being ripped apart. It's forming this hot plasma of material, this accretion disk, that orbits the black hole and spirals down towards it. And this process produces a lot of light. Here in the disk, matter is being converted into energy, like the equation E equals mc squared. And if you think of processes that are a little bit more, let's say, thought of every day, such as the sun, right? Nuclear fusion going on in the sun does that same thing. But the efficiency of converting matter into energy is only about 0.7%. So 0.7% of the input matter is converted into energy in the sun. Now here, around a black hole, we're many times more efficient than that. This is about 40% of the input matter is now being converted into light. So a tremendous amount of radiation is being produced here. And in the accretion disk, we're producing ultraviolet light. So the same type of light that'll give you a sunburn. The amount of light coming out of this system is like scorched earth situation. This is not a sunburn anymore. This material is about 10,000 degrees Celsius. However, as we move closer to the black hole, the orbital velocity, the rate at which this matter is orbiting the black hole, increases. And in fact gets so high, and the material gets so hot that it's no longer producing just ultraviolet light. It's now producing X-ray light. And we call this area the corona of the black hole. And this is by far and away the most extreme environment around the black hole. 1 billion degrees Celsius, right? Billion degrees Celsius. Extremely hot, produces X-ray light similar to that that's used in the hospitals to take images of your bones. And in fact, this area is where things get a little difficult to think about. We don't exactly know what this corona looks like. Here I've represented it as the innermost part of this accretion disk, but perhaps it might actually be more of an atmosphere type thing, or perhaps it's some compact source near the black hole as opposed to this stretched out part of the disk. At the moment, we don't know, but this is something that I worked on a little bit for my master's thesis. Well, I shouldn't say a little bit. I did a thesis on it, so I did a lot of work. And so if you want later on, we can talk about that. But for now, this is what we want to consider. X-ray emitting region, UV emitting region, and there's this accretion disk around the black hole. So at this point you might be asking, all right, that's a nice, interesting looking schematic. Let's see some beautiful pictures. And so I just want to highlight to you that there's a little bit of a problem with taking a picture. And it's due to the fact that even though this is a supermassive black hole, and it's actually quite large when you try and place it in our solar system, the region itself in comparison with the galaxy is very small. And so if you bear with me for some of these numbers, I've kind of cherry picked them, but we'll hopefully clarify that in a few slides. If we take a mass, let's say 6.5 billion times the sun, the region, this accretion disk, would have a radius of approximately 640 astronomical units. And so if this is placed in a galaxy that's, let's say, 16.5 million parsecs away, so further away than Andromeda, but not as far away as the first object we were looking at, the angular size on the sky of this region of the AGN, the central engine, would be 40 micro arcseconds. And for those of you that don't know what a micro arcsecond is, this is the equivalent of, from where we're sitting, trying to measure the size of a golfing tee that's been placed on the surface of the moon. So this is an extremely difficult task that, if it were to be done with an optical telescope, would require a diameter of about 4 kilometers. So completely absurd sizes here. And so to put this into even further perspective, let's take a look at this galaxy here, M87. M87 is roughly 35,000 parsecs across in visual light. The central engine that we were just highlighting, I said, is 640 astronomical units. So 640 times the distance from the sun to the Earth. And if you convert that into thousands of parsecs, you get 0.000003 parsecs, or kiloparsecs, excuse me. Extremely small. So, as I said, this cannot be observed with conventional telescopes. So, some of you may know where I'm going with this. It's a good thing that people think outside the box from time to time. And astronomers came up with this, essentially, telescope. This is a collection of 8 telescopes from around the globe that are used to make a telescope with the effective resolving power of about the size of the planet. And so what happened here is that these 8 telescopes simultaneously observed the center of M87 in April of 2017. Actually, tomorrow will be the 5-year anniversary of those observations. And without further ado, here are the results. The very first ever image of the inner region, the central engine of an active galactic nucleus, an AGN. And what we're seeing here at the very center is the shadow of the black hole in M87 called M87 star. And the reason this image looks the way that it does is due to the significant gravity warping the space around this black hole. And so the reason that the bottom of this image looks a bit brighter and yellower than the top, which looks a little faded, is because as the material in the disk is orbiting, the material coming towards us appears brighter, and the material moving away from us appears dimmer. And so if we go back, I'll let you know that all those numbers I used to calculate the size of the central engine before, those are exactly taken from M87. It has this black hole mass of about 6.5 billion times the sun. It's about 16.5 million parsecs away from us. And the 640 astronomical units are roughly about this size. So we're truly seeing here the central part of the AGN, which is remarkable. This is something that's never been imaged ever before. We've only had to rely on our simulations and our models to produce images like this. And I'll let you know that this looks exactly like what we thought it would look like. So truly a testament to both the observing power that we have now, as well as the accuracy of some of the theory that we've been able to come up with. Well, not me exactly, but others. So just to put this into another size perspective here, we have the solar system. So we put the sun at the center where this black hole is, and you can see Pluto's orbit, completely dwarfed by the size of this black hole. And in fact, the inner part of this accretion disk is nicely represented by about how far away the Voyager 1 satellite is from Earth at the moment. So about 150 astronomical units. So truly a massive, massive system here. But again, compared to the galaxy itself, quite small. So we've highlighted what AGN are and how they work, but perhaps now it's time to ask the question, okay, so why does all of this matter? And the reason is actually in the fact that these two galaxies look different from each other. We have M96 on the left and this other galaxy, IC 2006, on the right. And what I want to point out is the formation of stars. In M96, there are tons of new stars, and you can see them as the blue light in this ring around the galaxy. In IC 2006, we don't see any of that blue light. And it's not just because there's no blue light filter here or anything like that. This is the same type of image. There's just nothing blue. And so why is that the case? So that would indicate to us that there's no new stars. And in fact, calculations show that new stars stopped forming here about 10 billion years ago. And the universe is only about 13.5 billion years old. So this is a very long dead galaxy. Why is that the case? What makes these two things so different from each other? And we'll take a quick aside to talk about star formation very briefly. And we'll get back to that. So the formation of stars, right? You need molecular gas clouds with some set of parameters in order to go through a process and form a star, the sun here on the right. And so I will just highlight to you that in order to form a star, you require low temperature, high density molecular clouds. Anything else, and you won't make a star. That low temperature, high density cloud will start to collapse in on itself, and the temperature will increase and the density will further increase, eventually resulting in the production of a brand new star. And so to get back to our AGN, what do AGN have to do with the formation of new stars? And in fact, now what I'll highlight to you is that AGN outflows, the outflow of energy and material in two types of systems, jets and winds, can actually dramatically alter the course of star formation in the host galaxy. Okay, and just recall, we often think about AGN or these black holes as little cosmic vacuum cleaners sucking everything up around them. But now I'm going to highlight to you that that's not always the case. They in fact can eject a lot of energy and matter as well. And so to start, we'll take this beautiful image of Cygnus A, which highlights these jets that I'm talking about. So let's point out some key structures here. The center of the galaxy is this little blip in the center of this image, that little bright spot. And extending out from that central galaxy, you see these thin but long jet-like structures. These are the jet beams. These are the structures of very energetic, very fast-moving material coming out of the central engine around the black hole in this galaxy. And you might say, okay, how fast is fast? This is really fast. This is at nearly the speed of light. This is 90%, 95%, 99% the speed of light. So this material is extremely energetic. And as it makes its way along these jet beams, it'll eventually run into some resistance, some gas or some dust, and it'll start to slow down and it'll start to deposit its energy. And that's what we're seeing in these big plumes of radiation at the edges of this image, these energy deposits. And so to give you a size perspective of how large this is, I've placed the Andromeda galaxy in here just for reference. This jet beam, one side of it is about 75,000 parsecs, or about 15 billion times the distance between the Earth and the Sun. The entire Andromeda galaxy and its collection of stars is about 42,000 parsecs across. So this jet stream is several times larger than the entire Andromeda galaxy. So these systems are not small, despite the fact that they're coming from an extremely small portion of the host galaxy. This is starting to get into not just the space outside the host galaxy, this is starting to get into the space between galaxies, right? Recall, Andromeda is about 10 times further away from the Milky Way, from us, than the size of this jet stream. So sure, it's further away than the size of the jet stream, but we're starting to get into that kind of territory. This is starting to deposit energy that could affect neighboring galaxies. And so now you might have the question of, okay, what is this jet? How does it work? What's going on here? And the answer is, without getting into too much complicated theory or anything like that, is what we think of as magnetic fields. We think it's probably due to magnetic fields. And so here's an image many of you may have seen before, or if you have ever done things like this in high school, playing with bar magnets and iron filings, this is what we're seeing, right? So you have a bar magnet as the red rectangle and the iron filings around it. And the shapes that the iron filings are aligning themselves to are exactly the magnetic fields of this bar magnet. So they connect from the northern pole of this magnet down to the southern pole. Now, if you put these two magnets, or two of these types of magnets together, you might get a magnetic field arrangement, something like this. And what I want to highlight to you is specifically what's happening at the center, going up and going down. You have these magnetic field lines that are pointing almost straight up and almost straight down. And so you might imagine that if you put your black hole at the center and your accretion disk in there as well, harboring these magnetic fields, you can imagine that some of the material that drops off the disk and moves for the final time towards the black hole might get caught in these magnetic fields. And if it does, it'll get launched out at nearly the speed of light from this system. Remember, these are extreme, this is an extreme environment. What's going on around the black hole is very far away from anything normal. So this power that's produced by the magnetic field around this black hole has the ability to launch the material at almost the speed of light. And so here are some nice videos highlighting how this jet looks and how it propagates in this featureless medium in this box here. So before we get playing the video, what I want to highlight is the scales here, the size scales. So just again to highlight how small the AGN engine truly is. The vertical and horizontal axes in this plot are about 200 parsecs in size, or about 40 million astronomical units. Recall, our AGN in M87 is about 640 astronomical units. So the black hole and accretion disk and all that goodness that we went through in the beginning slides, that's not visible. That's very, very small in this plot. And so if I play the video, let's wait for it. So hopefully you guys can see that with a somewhat decent frame rate. What you see moving horizontally is this dark blue stream. That's the jet that we've been talking about. It's extremely energetic material moving out horizontally out of the central engine into the host galaxy. And as it burrows its way through the material in the host galaxy, you can see this cocoon of red forming around it. That's this high density shock wave that's moving through this smooth, featureless gas in this simulation. And so here's some snapshots of it in case you weren't able to view it with a smooth frame rate. But moving on, we know that galaxies are not made of smooth, featureless material. They're clumpy. They have clumps of gas, clumps of dust, star clumps. And so what happens if you put this jet in a system that looks a little bit like that? And in this video, so everything about it is exactly the same, except we now have some new clumps of gas. So if I pause it right at the beginning, exit this thing, what you see are these red pockets. These are these high density, low temperature pockets of gas. Let's see what happens when we turn on the jet. So immediately what you notice is as the jet is trying to burrow through, there's a lot of dissipation of energy in this cyan light blue color as the jet fires its way through the central portion of this galaxy. And as it does that, the entire galaxy heats up. A lot of these gas clouds get energized and their density decreases, and the entire system is disrupted by this jet. It's mainly focused along the jet direction, but it's clear that the entire system is disrupted by the jet. And so just some snapshots again, in case you weren't able to view that with a good frame rate. Here we see the evolution of this jet as it blasts its way through this poor galaxy. And so recall what I mentioned earlier about star formation. We specifically needed low temperature, high density material. The jet's ruined everything. It's taken all those nice clumps of star forming material and it's wrecked it. So it's turned off the star formation in this galaxy. It's completely shut it off. And so here's an example of how the central engine so the very small region around this black hole can completely change the evolution of the host galaxy. All right. And so some of you might be asking, some with good eyesight might be pointing out that, okay, that looks to be the case for most of the gas, but in fact, there still seems to be some pockets of gas that are pretty dense. They're pretty red, right? In this image, they're pretty red. And so is it possible that stars can form in those pockets? The answer to that question is yes, it is possible. So on the vertical axis here, we have the formation of new suns per year. And on the horizontal axis, we have time over millions of years. The red curve denotes the formation of new stars with a jet, and the blue curve is without a jet. And the dotted line indicates when the jet in this simulation is turned on. And for this particular fine-tuned setup of jet and gas parameters, you can see that the jet actually boosts the formation of new stars for a short period of time, which is really interesting. This is something that's relatively new. For a long time, we thought that the jet can only stop the formation of new stars. We weren't sure if it could ever have this type of effect. But in fact, in this simulation, what we're seeing is this boost in the red curve over the blue curve for a short period of time that greatly enhances the formation of new stars. And so if we think about back to that old dead galaxy I showed you a few slides ago, maybe this happened there. Early on, a jet turned on, formed a bunch of new stars, but then it ran out of gas. And so it stopped forming new stars, and it never has again because there's no new gas in it. Potentially, this is what happened there. And so that's jets. Now let's talk about the second outflow mechanism, winds. So this is M82 galaxy. And what you can see here is the host galaxy in the lighter bluer colors and this high velocity energetic wind. And immediately what you notice is that this wind is nothing like a jet. It is not focused in one particular straight line as the jet was. And it doesn't seem to extend to as large of a distance as the jet did. And in fact, the velocities of these winds is much lower than the jets, although still considerably faster than most other things that we think about. So this is about 10% or so the speed of light, as opposed to approaching the speed of light. And so, all right, what's going on with this wind? We can see that it's got a much wider angle, so it takes up a lot more space than the jet did, but doesn't go quite as far and doesn't deliver the same type of power or effect to the host galaxy. First, we'll take a look at how do you make this wind. And so what we have here is the process by which energy from light or momentum from light is transferred onto an atom. And so what we see here on the left is that light has some momentum indicated by the equation there. The lambda indicates that the shorter wavelengths of light contain more momentum, okay? So as this light is absorbed by the atom, it energizes one of the electrons, potentially even ejecting it from the atom, but it also transfers a small amount of momentum, a very small force to that atom. And this is on a daily basis, this happens all the time. If you have a light source near you, this is happening. The issue is that, or I guess it's a good thing that it doesn't actually have a significant effect on our daily lives. This is an extremely small amount of momentum transfer. And so what's happening here is that if you increase the energy of your light or you make it shorter wavelength, you can transfer more momentum to it. And you might see where I'm going with this. If you have these gas clouds around your central engine, and so I should mention that this is the central engine. If you think of the disk before, that was seen face on, so you're looking down across the entire disk. Now, if you tilt that system about 90 degrees and you're looking at it edge on, this is that situation. And so what we have here is lots of X-ray emission from this blue corona, lots of ultraviolet emission from this outer part of the accretion disk, and it's going in and exciting all this gas. And recall, this central engine is 200 times brighter than Andromeda, so it's trillions of times brighter than a star. And so this radiation force is capable of driving out this material at a significant fraction of the speed of light. Once again, 10% the speed of light. And so what does it look like when we think of these simulations that we saw before? So again, everything about it's the exact same, the same scales, but instead of a jet, we now have a wind. So let's see how this wind propagates through this featureless medium that we were looking at with the jet before. Immediately you notice that there's no high density cocoon around here. There's no red. This is all energetic, fast moving material forming now, instead of a streamline, this is forming a bubble of material that's just billowing out of the region around the black hole, okay? And so again, if you didn't have a good frame rate, this is just a snapshot of each time in the simulation that was conducted. So once again, galaxies are not featureless gas clouds, they have clumps. And so what happens if we put it in a clumpy medium? So a spherical distribution of gas. What you can see in this simulation is immediately the wind is much more disruptive to the galaxy than the jet was. That energy dissipation is far more efficient for the wind than the jet. Now, sure, the jet can reach outside the galaxy much more rapidly and much more easily, and for a longer period of time. But the wind is more effective at disturbing the gas clouds in the host galaxy. So here, if we contrast it with what we saw with the jet, there was lots of red at the end of that simulation, lots of dense, low temperature gas clouds by the end of that simulation. With the wind, you don't see anything like that. There's hardly any available. And so here you might come to the conclusion that, okay, then that means a wind would definitely shut off the formation of any galaxy that has a wind in it. And that's where I want to point out yet another simulation, the last of these simulations, which is, what if instead of a hemisphere of gas clouds, kind of like an elliptical galaxy, what if we had something that was like a disk of gas clouds, like a spiral galaxy might have, like our own, the Milky Way? This is what happens in a spiral galaxy. You can see that the wind very quickly blows its way through the central gas clouds, and it starts to make this characteristic bubble. However, as this bubble evolves, you can see that it's starting to press back down on the disk. And as it does so, clouds that may not have been dense enough to form new stars at the beginning of this simulation are now having enhanced density such that they're able to form new stars thanks to this wind. So in this scenario, similar to what I showed you for the jet, it might actually be possible for the wind to enhance the formation of new stars, which is incredible. Again, this is something that we weren't really sure could happen. These outflows, why would they help to form new stars? All they're doing is depositing energy into this system. How could that ever help to form new stars? And very clearly here, what you're seeing by the end of this simulation are dense pockets of potentially new star formation. And now we're nearing the end of the talk. And so what I want to tie this back to is the very beginning of the presentation. Notice what both types of outflows had in common. They both had a similar system at their core. And that system is based on the inflow of matter. To drive this outflow of material, you required as the very beginning building block of these outflows, the inflow of material. Just want to leave you with that there. And so that's the summary. This is the summary now of my talk, and that's what I wanted to talk to you about today. And so just to highlight some of the key points that I presented, they are that active galactic nuclei, these AGN, are the most luminous continuous sources of light in the entire universe. And this is a result of the inflow of matter from the center of the galaxies that host these supermassive black holes and the conversion of that matter into energy. And so while we often think of black holes as little cosmic, or not little, I guess, they're supermassive, right? These huge cosmic vacuum cleaners, we now see that they have a huge potential to eject a tremendous amount of material and energy back out into the host galaxy. And that this effect, this outflow of matter and energy, has a huge role in why the universe looks the way it does today, why we have these old red and dead galaxies, and why we have more star-forming galaxies. This is the AGN activity is precisely linked to why the universe looks the way it does today. And so thank you very much for your attention and for having me here today to talk to you about some of the work I've done. And I'll take any questions that you might have now.
Okay, we'll open the floor. There's nothing in the chat at this point.
Okay.
But I have a question for you that may not be answerable.
Sure, okay, yes.
You've noted where these galaxies have these outflows. Have there ever been any acknowledgement or sight seen of two sets of outflows from different sources coming together?
Oh, that's a good question. So you're talking about like two jets interacting with each other, right?
Correct. No,
right. So
M87, for instance, the example that you've got there, if it came in close, well, galactic close proximity to another with its outflow, has there ever been any instance where outflows have met, and what would be the consequence thereof?
So that's an excellent question. Off the top of my head, I can't think of any examples of that, but there's a few things that I didn't mention here, and that one of them is that the activity of the AGN has some sort of life cycle, right? So it'll start and it'll end after some time period. And so there is presumably has been some time in which such things have happened. And the systems in which we observe these really powerful large jets are typically in clusters of galaxies. So where galaxy membership is in the hundreds or thousands of galaxies in near proximity to each other. Now, what we usually see is that only the largest centermost galaxy in those clusters is producing these large jets. And so, as I mentioned, off the top of my head, I can't think of any examples where we've seen two jets interacting with each other. But if it were to happen, it would be in these cluster type environments.
Thank you. Anyone else with a question? Oh, sorry, Jerry, go ahead.
Yes, I just wonder, I don't know if you can hear me. Can you hear me?
Yes, I can hear you.
Okay, so how does the more recent image of the magnetic lines or affect this this thinking?
Right, yeah, that's a really good question. So for those that aren't aware, there was a very recent, I think it was 2 weeks ago, publication of a brand new image like the one on the right here, except superimposed on it are the actual magnetic field lines in the disk that were measured. And those magnetic field lines form I don't know if you can see my mouse or anything. Can you see this wiggling around? Yeah, okay. So those magnetic field lines form a little spiral pattern along the whole disk that points in towards the black hole. And so what those images are showing is, number one, that there's certainly magnetic field activity in M87, and M87 does have a jet. So this is very promising that we see this magnetic field activity at the very center near the black hole and the presence of a jet. And the results of that work actually showed that the accretion disk is being significantly affected by the presence of this magnetic field, such that if you remember my little diagrams there showing the like kind of focusing outward of the magnetic field from away from the accretion disk. And so what those new images are showing is that the magnetic field actually produces a lot of resistance to the inflow of matter. And so what's happening in M87 that we think is that as material is inflowing from the outer part of the disk, it reaches a certain point where it suddenly becomes very difficult to move inward due to these magnetic fields in that image. And so what happens there is that the material spends more time in the zone where it's converted from matter into energy. And so what they're thinking is happening is this slowing of the inflow is allowing for more of the matter to be converted into energy than would normally be possible. So hopefully that kind of answers your question a little bit.
Okay, just see. Okay.
There's a question on the chat.
Yeah, I've got a question from the chat from Brett, who says, on slide 39, the one where the jets cause a spike and then drop in star creation, what
Right.
accounts for the spike? The increased density? And if so, wouldn't the increased temperature of the jet offset that star creation effect?
Yeah, so that's a really good question. I looked a bit into the specifics of this type of simulation, and one of the difficulties with simulations where we try and examine the effect of a black hole on the entire host galaxy is that it's extremely difficult to get all of the physics and all the size scales correct. And it relates back to the size scale, right? So if you recall, the black hole region is extremely small compared to the host galaxy. And so when you try and include the effect of a very small region on a much larger region, and you're trying to do that with a high resolution in your simulations, you have to make some trade-offs somewhere. And so the authors of this work in the bottom left here, they have to leave some things out because we can't include all of the physics that we know. And there's also some effects that we might not yet know of that could be affecting this. And so what I'm trying to say is that for this specific setup of parameter inputs, it was possible to create, or to enhance the star formation for a short period of time with the jet. And so what might be happening here is that as the jet turns on, it creates a shock wave that rippled out from the center. And for that short period of time, not a ton of energy is propelled by this jet into the host galaxy, but a shock wave is propelled that can enhance the density of those clouds. And so what might be happening here is that the shock wave that's moving through the galaxy quickly enhances the star formation, but as the jet deposits more and more energy into the galaxy, it very quickly runs out of new, cold, dense gas to form new stars. So hopefully that answers your question.
Okay, and we have another one from Colleen, and Brett says, thank you, cool. Colleen asks, in the inner part of the accretion disk where 40% of the matter is being turned into energy, what is the process? Is it fusion like at the center of the sun?
That is a good question. No, it is not fusion. This is essentially matter being ripped apart. So this is like the nuclei, the essence of, so if we go to this atomic structure here, right? This, in fusion, you're going to slam the two atomic nuclei in the middle and on the right. You're slamming those together and you're forming a new one. So in the sun, two hydrogen nuclei are slammed together. They form helium and that emits some energy. What's happening in the active galaxy or beside the black hole is that this material that started far away, as it's making its way toward the black hole, is losing what's called gravitational potential energy. It had more potential energy out here than it does in here, and that loss is being converted into light. Further, the atom is actually being torn apart. It's just being shredded. And as it does that, the binding energy of the nucleus and those things like that, that's being released out as energy. Okay, so it's literally the conversion of matter into the energy that's keeping it together.
Well, that's great. This has been absolutely fascinating. I think between you and Dr. Gallo over the last 2 months, our knowledge of black holes has certainly been greatly enhanced. And we really want to thank you for this, Adam.
Oh, thank you so much for having me.
And putting it into simplistic terms that even folk like me who aren't scientists by nature can actually understand. So
That's great to hear. That's great.
If there are any further questions to Adam, you can put them in the chat, and if before he leaves, we can have him answer them. Otherwise, we will email them to him and he will answer you individually, if that's okay with you, Adam.
Oh, absolutely. Yeah, for sure.
Okay, thank you very much.
Thank you. I'll stop sharing my screen.
Okay, so next on our agenda are two speakers, two of our members, Dave Chapman and Melody Hamilton, and they're going to be addressing the RASC Double Star Observing Program. And to give you a brief introduction as to who they are, ladies first. Melody Hamilton is a contributing member of the RASC Observing Committee at the national level and has certainly served in the past here in Halifax as our vice president on our board of directors and as chair of Nova East Star Party. She's an avid observer, and I'm sure that those of us that know her can all agree she's probably one of the most, if not the most, accomplished observing members in the country, having completed 6 out of the 8 observing programs that RASC offers. And I'm quite sure she's probably in the business right now of trying to complete those 2 as well. She's also a member, by the way, of the Minus Astronomy Group, which is another group here in Nova Scotia. And Dave Chapman was a member of the Ottawa Center when he was a wee lad of 10, way back when. After all, you already did tell us, Dave, that you were old. And he actually joined the center in 1984. He's now serving on both the RASC Observing Committee as well as the RASC editorial board. And he too has served in numerous capacities here in Halifax Center. And in 2020, actually a year ago, he became a member of the fellow of the RASC. So I will give it to floor over to both Melody and Dave. Welcome.
Well, thank you, Judy. I'm wondering, is Melody there? If she's there, she's joined by phone, but I don't see her.
I don't either, to be honest.
And I didn't notice her, and so I called her a couple of minutes ago and couldn't raise her. So obviously something has come up and she can't join us, which is too bad because she's got some stories to tell. So I think what I'll do is I'll just struggle on without her. But I want to say that Melody is probably much more qualified to speak about this than me, because she started working on the Double Star program, and the last time I talked to her, she only had a few left to go. So, and I've only done a handful. Anyhow, I do have a presentation I can share, and I can say a few words about the program. So I'll try to do this screen sharing thing. How are we doing? No, that's not going to work.
It's showing.
Try that again. Ah, okay. So we can see it and you can hear me, right?
Yes.
So I'll try to keep this brief. A couple of years ago, more than a couple of years ago, when I was chair, or maybe even before I was chair, there was talk about doing a new observing program. And Blake Nancaro from Toronto said, you know, let's do one on double stars. And at some point, it became, when we were doing strategic planning, you know, we had a bunch of different objectives. And I think we put that down for the observing committee nationally, that one of our strategic plans objectives would be to introduce a new observing program with a certificate. And that became, that's what the Double Star observing program became. It took a while to get here. turns out it's more complicated than meets the eye. And but anyway, it was launched there earlier in the year, or last fall. If you want to read the official account of what the Double Star program is about, there's the link at the top of this slide. Now, these slides about the Double Stars observing program are appended to my WhatsApp presentation, which will come later. So if you go to Halifax, RASC Halifax website and find the WhatsApp, you will find the presentations, both of them, and the PDFs you can read, and you can see all the material that I'm presenting here. So you don't have to scribble it all down. And all of the links are active. So that's where you can go to get the information. There's a lot to read if you want. So there on the RASC site, there's the official program with all of the documents and the forms and the application form and so on. Now, recently, in the latest journal of the RASC, Blake Nancaro wrote an article about the program as well. So you can read that. And also recently, Melody, with help from me, wrote an article in our Nova Notes. So you can read that. And if you read all of that, you probably know more about it than me. So there's lots of information there to get you started. But I'll just run through this and try to give a little promo. So the basic facts about the program is that there's 110 objects. And that number 110, it comes from, the Messier catalog is 110. The finest NGC was set at 110 to match the Messier. So the Double Stars program, it was chosen 110 to match the other two. So there's 110 objects or targets, and they range from easy to challenging. All must be observed and logged. There's no options. There's no getting around it. So if some are harder than others, well, you just have to go back and try again. But all the ones that I've looked at have been not hard, but I've only looked at a handful. I wish Melody were here to comment about the difficulty, but in view of the fact that she's almost finished, I imagine that they're not all that challenging. You only need a small to medium-sized telescope to do these. They're not faint. They're all a decent magnitude. And because I'm observing from my backyard here in suburban Halifax, and Melody's, of course, is observing from her lovely rural site down there near Digby, with their nice little observatory. So she has very favorable conditions. But I have to say that this program is moonlight and light pollution friendly. In other words, the presence of the moon and light pollution will not interfere, except I would say in the manner in which you find the stars. Now, Melody is a star hopper. She's not a technical person. She doesn't use GoTo. She's old school. She goes and finds the main stars and star hops. I confess that in the backyard, I can't even see enough stars to hop between them. So I have a GoTo telescope, and I unashamedly use GoTo at least to find the bright stars that are close to where the targets are. But I have been using GoTo, and there's nothing wrong with that. Your certificate will indicate whether you used GoTo or traditional methods if you complete it. So there is a certificate, and I would guess that if you worked at it, if you worked at it kind of a medium level, it would probably take you about a year, because you can do a few a night. Okay, and like I say, the only thing that would stop you, I guess, would be cloud cover, because you don't have to stop observing, because the moon's out. You don't have to stop observing because there's light pollution. So, if you have a few, a clear evening, you should be able to snag a few double stars. The few that I did, I was looking at them last fall when I was observing Mars. I would observe Mars for a bit, and sometimes the conditions weren't right. So I'd say, well, I'll come back in an hour, right? And see if the seeing conditions. And I had my telescope set up in the backyard with a hood over it. So in between observing Mars, I would say, well, let's try finding some of those double stars. And I would find which ones I could see from my yard. And so that's how I started doing it. I was kind of doing that on the side while I was observing Mars. It was a lot of fun. So as I said, the documents are there. So there's quite a lot of documentation for this, and people get a little bit lost in it. So I'll go through this. There's what's called a quick start guide. And this is for people who just can't wait. You know, they don't want to read all the stuff. They just want to get going. That's for you. There's a quick guide. So you just like, you feel like you know what you're doing and you just want to get out there and start observing, go for it. If you need a little more background before you start, there's the full guide, which is 12 pages with everything you'd want to know. And that includes the main list of 110 objectives. I mentioned that they're essential. Now, here's the thing, and this has confused some people already. There's a main list of 110 objectives. However, the way Blake has set it up, it gives you the name and the position so you can find it. And it tells you what the combined magnitude of the star is, but it doesn't say anything else about how many components, how far they are apart. All of that stuff is not there. It's just, this is the name of the star. This is where you find it. And it gives you some idea what the magnitude is. So the idea is you go and have a look at it and see what you can see. And more often than not, when you get there, you see a field of stars and you say, oh yeah, there's the double star. And so, you know, you have a look and you describe it, you write your notes or make a sketch, whatever you want to do. And then the idea is, this is what Blake wants you to do anyway, is to kind of discover it and find out what you can see. And then you go back and you can look up the supplementary list, which was a second list, and it has got all of the components, the magnitudes, the separations in arc seconds, and the position angles. So that lays it all out. And that's how you sort of follow up your first observation to see what you saw. Now, I believe you only actually have to see the primary and secondary stars. Sometimes there's multiple star systems, but I think you only really have to see two, but I have to check that. Now, you don't have to do it that way. You could just say, well, no, I really need to know what I'm looking for. So you can use the supplementary list, say at the telescope, and when you go to the star field and have it all laid out there. But, you know, I've tried it the way Blake wants it, and I actually enjoy it. I feel that doing it that way makes it way more fun because there's that element of discovery. Like you're being told where to look, but you're not exactly sure what you're going to see. And Melody agrees with me on this. If she was here, she'd say, I agree, Dave. So the supplementary list has everything you wanted to know. There's a variety of ways to log these things. There's different log books and pages you can download. And there's some observing lists. And what I mean by observing lists is, for instance, SkySafari is an observing app, and you can create an observing list within SkySafari and share that. Like you could give that to your observing buddy and say, here, put this on your SkySafari. And when you have it on your app, you can put that on your app and say, or highlight the targets on the screen, and it just shows you the things that are in that list. And then you can say, only show the ones I haven't looked at yet. So I use SkySafari, and I find it very useful. So I'm actually using the Sky list of SkySafari, and there's a couple of others. And I think there's an Excel spreadsheet as well. I've got a picture of an atlas here. I really think you need some kind of an atlas. It doesn't have to be a double star atlas, but to find your way around, you know, some of these stars, I wouldn't say they're faint, but they're not really bright. So I think you need to have a decent atlas or an app in order to, you know, in order to find your way to the proper star to observe. The Cambridge Double Star Atlas is a good atlas because it actually has the double stars marked on it, and it's got some information in the atlas itself. So I have a copy of that. So how to observe a double star? Well, it's like observing anything else. You locate it, you examine it, and you record it. So locating it, you take your double star from the checklist, you note the combined magnitude. Sometimes there's suggestions about aperture and magnification, but whatever you like. I mean, if you find that the magnification isn't enough, then put in a higher magnification. So basically the first stage is to find it and to make sure that you're in the right spot. That can be a bit tricky at times, but more often than not, you say, oh yeah, there's the double star. That's what I'm looking for. I mean, that's my experience anyway. They're not, they're not too subtle. So the next thing you do is study it and examine it. So you view the star field at low power, ask yourself the questions. Is it obvious? Is it the double star, the multiple star? Am I in the right place? Do I need higher magnification? How many stars are there in the field? How bright are they? Did they show any obvious color? That kind of thing. So you just kind of have a look, and then this is the point at which, well, actually I'm getting ahead of myself, but you just kind of view it and see what things need to be noticed. One of the things that's good to do, regardless of what kind of telescope you have, is if it's a driven telescope, turn off the drive and just see the way the stars drift. So if you've got your bright star or your target star in the middle of the field of view, turn off the power. Or if you're just using a push-to telescope, you don't have to do anything. You just let it drift. Regardless of what kind of mount you have, regardless of what telescope you have, how it flips the image around, if it's a Newtonian, a refractor, or erecting diagonal, doesn't matter. Those stars are going to drift. The star in the middle, say, is going to drift and go to the celestial west. And that's worth remarking because, like I say, it's regardless of how you're observing it. And it's good to know the directions in the eyepiece. If you're in a standard optical configuration like a Newtonian or a straight through refractor, celestial north is 90 degrees counterclockwise from west. If you have mirror reverse optics like a star diagonal, a regular star diagonal, so you're using a refractor or Schmidt-Cassegrain, north would be 90 degrees clockwise from the west. And position angle is measured from north counterclockwise or clockwise accordingly. Now, they don't ask you to measure any angles, but they do like you to mark down whether it's, northwest or north or south, the sort of the cardinal direction. So that's why it's good to kind of figure out what the directions are. Once you've done this for your eyepiece and your telescope configuration, you get pretty used to it, right? Once you figure it out, it takes a little while to figure it out, but once you figure it out, it's just going to be the same for every observation. So then you want to record, and what Melody and I both recommend from experience, and we did this completely independently, we recommend that you simply draw the star field. It is the easiest sketch of life. It could be easier. You draw a circle on your little sketch pad or your observation form. I have a little pill bottle top that I use to draw a circle. So then you look in the field of view and you draw a star field. You make big dots for the bright stars and little dots for the faint stars. And you use you kind of create patterns and triangles, and you just try to draw in rough form what the star field looks like. Like I say, it's the easiest sketch of life. It's putting dots on paper. Don't tell me that you can't draw and you're not an artist. We're putting dots on paper. Now, the only people who have an excuse, somebody who's up in the Yukon said, when I'm at my telescope, I can't take my mitts off because I'll freeze. I said, okay, you get a pass, but you have to come up with some way of recording, your star field. I can see why you might not want to sketch. So the alternate way of doing this is you can describe the star field in words. Now, if that's something that you prefer, if you're more of a verbal person, you can do that. Maybe you could even have a little tape recorder or your your voice memo on your phone, whatever. You describe the star field in words. Either way, you have to make a record of what you saw. So you need to talk, you have to identify the stars, the brightness, the color, the orientation, and the relative distances. This is all qualitative stuff, okay? You don't have to have measurements, but just like, these are Melody. I'm going to show you a bit. Melody came up with some words you can use. And you should also record the circumstances, where you are, what the date is, the time, sky conditions, telescope, all the usual stuff. I also record who I'm with, which is mostly nobody, but it is nice when you are observing with somebody to make a note of it because it's fun to look back and remember that. So here's an example of mine. So what I did here is, now this is the final drawing, but basically what I did here, I directed myself to the star. Now this star is HD 196411, which is a catalog number, and it's in Delphinius, okay? The constellation Delphinius. So I found the star and I saw the star field. I said, well, this must be what we're looking for. So what you do is you draw everything you see and you make notes and you let the thing drift. If you look closely at my drawing, you can see my original arrow said this is westish, in the field of view. I went back later and put those crosshairs. So you identify the components. So what you do is then what I do is I go back inside and look at the list. Time for a coffee, warm up, go inside, open up the supplementary list and figure out what you saw, identify the different components. A would be the primary, B, C, D are the ones that are farther away. And then you don't, like I say, if you have the sort of the rough idea of where things are, at that point, what I do is I put that crosshairs on the drawing because I know which way is west. So I put a line through star A, and then I turn it 90 degrees and put a line crosswise to that. And because I was using a Newtonian reflector, I knew that north was counterclockwise from west. And so I just marked that north and west. So now I know where all the cardinal directions are, and I know which way the position angles are measured, and I have some idea of the relative distances. So you identify the components from the supplementary lists. And I've written down, I had a Skywatcher 300 millimeter telescope, f5. I used the Teleview 6 millimeter radian. The seeing was poor. I saw no colors. I'm not good at color. Some people are. And I basically said that they all kind of looked identical to me. And I said A, B, C were obvious, and D, I have to admit, I think I had to go back out and find D, but it was very faint. I went back and said, oh yeah, there it is. Anyway, I think I did okay. Melody said I did okay. So up in the corner there, I got 0.27. I think that's degrees. That's the field of view of that telescope and eyepiece together. So that's my observation. I don't know if it's enough for the certificate, but that's as far as I've got with it. Maybe I'm going to have to go back and get the official forms, and I've got the date and the time, all that stuff. So Melody said for the distances, she has this range of words that she found. Extremely wide, very wide, wide, pleasingly close. That's an interesting one. I didn't get a chance to ask her about what's the difference between close and pleasingly close. In fields other than astronomy, I know how that feels, but I don't think that's relevant to this discussion. Very close, tight by a tiny gap, touching or kissing. Figure 8 or peanut. So that's when they're getting really close. And rod shape means you really can't distinguish them. So there you go. There's some natural language expressions you could use. So here's Melody. She's using the official forms. And I'm sorry she's not here to explain this, but you can see that she drew, this is a different star, by the way. But you can see she's filled out the form properly. She's got all the different things there. And she's also got a very long description in addition to her sketch. And one thing I wanted to point out to you is that notice that her north, south, east, west is flipped from mine. So I was looking at Newtonian reflector, and she's using a Schmidt-Cassegrain with a star diagonal. So her representation of this is flipped, but she's drawing what she sees. But at least she's written down the directions, okay? So I don't know how much more I want to say. Like I said, I wish Melody were here. It's fun. You know, there's some work to do, and you might learn a few things about double stars. And I think that's all there is to this presentation.
Thanks, Dave. There were a couple of questions.
Oh, yeah.
One from Brad says, I'm guessing Alcor and Mizar would be considered too easy. And Bob says, and Alberio?
They're pretty easy. I honestly, I don't know. They must be on the list, because Alberio is a colored double star. I think there's some dispute about whether it's physically a double star or not, but it might be on the list. I haven't. I don't know. I'd have to look that up.
And I'm assuming next question.
Alcor and Mizar. The thing is that I think I always get them mixed up. Alcor itself is a true double star, and Mizar is there as well. So when you look at them in a telescope, you see Alcor and Mizar, but then Alcor itself is double, and there's another star in the field. So that's an interesting one. I bet you that's on the list.
And probably in response to your comment about the fellow from up north who couldn't take his mitts off and couldn't sketch, Bob Russell asks, what about taking an image?
It's a visual observing program.
I know, but in terms of, perhaps Bob's question is, take a picture of it and then you can go inside and sketch it.
Yeah, anything that would work. I wouldn't want to encourage people to hand in a photographic atlas.
No.
But I think that's a good question. I'm going to flip that back to the observing committee, because we're getting a lot of similar questions, and I guess there is an initiative afoot to do enhanced astronomy. I don't know how far that's gotten. I'm guessing not very far, but the observing committee is very much, there's a range of opinion, but the observing committee is very much about visual observing. We want people to put eyes to eyepieces. So if there's some easy way you can snap a picture to help make your record, that's great. But we wouldn't want to see photography replace the visual observation, okay? Because it's too easy to make out a faint star. We want people to be all on the same playing field here. We want people to do visual observation. Yeah. I'm going to take that under advisement. Yeah. I would cautiously say it would be okay, but don't even think about submitting a photograph as your observation, okay?
Yeah, he was saying use an iPhone, an afocal image for record keeping, perhaps.
It would be interesting to see if it would even turn up. I haven't even tried that. Okay. I might try that. I think you have to have a baby. Well, somebody should try it, and just I'd be interested to see what they come up with.
Okay, thanks, Dave. Could you stop sharing your screen at this point?
I can. We're done, yeah?
Yeah, thank you very much.
You're welcome.
Okay, so next on our agenda is something brand new, and I'm going to share my screen again. And it's the members' question period. Oops. Let's see if I can get this here. This is something brand new to our agenda. The board at its previous meeting determined that we wanted to start involving new members. And given the fact that we haven't been able to meet in person, so we're able to chat with these dear souls and be able to mentor them through some of the challenges they're having, we figured this would be an opportunity for them to provide us with questions that we could bring forward to all the members, because we were quite sure that there are other members that may have similar questions and would like to hear answers to these as well. So I would like to thank the three dear souls that did contribute to this. The first question up came from John Conahan, and he said, I'm very new to astronomy after receiving a telescope from my son for Christmas recently. I have a Celestron Nexstar 5SE with a 1.25 inch 25 millimeter lens. I've looked at some stars, but I don't know how they should appear when properly focused. It seems that I can see them almost as well with my binoculars. Is that normal? If you could send me a photo of how the star Sirius should look with a telescope like mine, that would be great information to have. To answer this, I've asked Dave Hoskin to answer this dear. So Dave, are you there?
Yeah, I'm here. Short answer is the star should look pinpoint, just like they look through your binoculars. Having said that, you may see some distortion if the telescope isn't properly collimated, which I don't think is likely the case since this is a brand new Nexstar 5SE. But even then, it would look just a little bit distorted as opposed to a pinpoint. And if you're using a fast Newtonian, towards the edge of the field of view, you'll see an effect called coma. So it'll look like the stars have little tails. But in general, you want to see a pinpoint of light. And that's because stars are so far away that it doesn't matter how much magnification you pile on your telescope, they're still going to be pinpoint. In fact, that's a good way to tell a planet from a star, because as you increase magnification of a planet like Neptune, you'll actually see a small disk, whereas you'll never see a disk when you look at a star.
So by changing the eyepiece, that won't affect his ability.
It won't affect, no.
Okay. Thank you. And I believe, if I'm not incorrect, you'll send him a picture of Sirius so that he can.
Well, yeah, I could, but that might confuse him, and I should say why, because when you take pictures of a bright star, if you look at a picture of a bright star in a book, it actually looks like a little disk, not a pinpoint of light, and that's because the sensor has been overloaded with photons, and it's spilled over to adjoining sensors, so you get what looks like a little circle.
Okay, thank you. Second question, and we did give members who asked questions the ability to remain anonymous. So this is from Anonymous. They said, I do enjoy The Moon at Noon and The Insider's Guide to the Galaxy very much. On The Insider's Guide, Chris Vaughn uses stellarium and is able to make a circle on his screen with the field of view for a particular telescope. Could you tell me how to do this with SkySafari Pro? Well, I went down the hall and asked the expert down the other end about how to do this, and he provided this for us. It's a short video.
Okay, here in SkySafari, we are sitting looking at the North American Nebula. We have a default cursor in front of us on the center of the screen. If we press the Observe menu item, we get to choose Scope Display and see the available fields of view that I previously defined. We're going to make a new one now by pressing the Add Field of View indicator. Within that, I click on the actual field of view editing field. I'm going to change that to 10, press the Done on the keyboard, and then press Done at the top of the menu. Having done that, if I go back to the Observe Scope Display, I can turn on that. Rather than clicking on it, we will slide it to the right and hit Done. Now we have a 10-degree field of view visible to us.
Thanks, Jerry. So thank you from Anonymous for their question. Jamie Wynot asks, if you are observing a few targets in one night, for example, the moon, is it okay to sketch one drawing of what we see and label the different targets on the drawing, as long as we include a description for each target? Dave, as observing chair, could you answer this one for us, please?
Yes. So I'm I mean, if you're observing a few targets on one night, you can do anything you want. But if you want to apply for a certificate, you need to follow the instructions of the certificate program. Now, there are no certificate programs that require you to sketch. So all the sketching is optional. You just, but particularly for the introductory ones, the beginners ones, you basically have to make a record of your observations so that the person reviewing it can satisfy themselves that you actually saw it. So the criteria are fairly broad, I would say. But if you're using one of the logbooks or log sheets, you may find that the circle provided for including a drawing, it might be a bit cramped if you're trying to put a lot of things in one circle. Now, other people have done their own thing, and instead of using the circle that's on the log form, they'll draw a big circle on another piece of paper. I think Lisa Fanning is one of the people that did that. She put multiple things in one picture, but you know, she gave herself a big circle so there was lots of room to draw things and label things. So you know, just basically use some common sense. The logbook for Explore the Moon in particular has enough individual spots that you can make a record for each individual feature. But if you want to simply sketch a group of features that are quite close together, and you feel there's room to do that, there's no problem with that. John Reed did that, and I'm actually doing that myself because I'm kind of using a small telescope, and I sometimes bundle together those things. So,
yeah. Especially if you look at things like, for instance, in the Gang of Four, for instance, if you're trying to locate that at a certain point in the moon phase,
yeah,
you may want to sketch them together, for instance.
But you know, you don't have to use the log that we provide. I mean, you can create your own system as long as just don't make it a headache for the person reviewing it. I'll give you an example, unnamed, not from here. Somebody did the Isabel Williamson and they made a PowerPoint presentation of their journey. And then he submitted the PowerPoint as his observing record, but they weren't in any kind of order. And that created some difficulty for the person who agreed to review it. And I think you have to help. If you're going to use different unconventional things, then you have to help the reviewer, you know, analyze your records. So just keep that in mind.
Okay. Well, thank you. That's the last of our questions for this month. But certainly new members and all other members are welcome to ask questions of us, and we will certainly make this an ongoing item each meeting so that we get questions from everyone across the center. So please feel free to forward your questions to us, and we'll be more than happy to address them for you. Yeah, okay, and I think I'm going to go out of this now, stop share, because that question regarding observing leads us wonderfully into the what's up. And Dave, we'll let you do your presentation now, if you would, please.
I was ready for you.
I noticed. Well done.
I saw a question before we do. I saw a question from Bob Russell, or a comment towards the end of the discussion about recording and all of that. And he mentioned it is, you know, his vision isn't the greatest. And that's a good comment to make, Bob, because I actually been thinking about this myself, because, you know, RASC is trying to be inclusive and all that, and be accommodating. So, you know, I think that I was going to talk to the observing committee about situations where there may be people who have, you know, who are differently abled, let's say, with regards to observing. And I was thinking of suggesting that we consider something like, by prior arrangement, somebody who feels like they cannot complete a visual observing program because of some reason or another, that if they kind of get it. You know, I would like to see a way that they can, by prior arrangement, work out something that's agreeable between the observing committee and themselves before they start, and then work on that basis. So, I mean, that's just the germ of an idea, but I thank you, Bob, for actually mentioning that, because it reminded me that I need to do that. I've been thinking about this for a long time, because, some people have sharp vision and other people don't. And it's really, really hard to see how somebody else looks at something. I mean, that's almost a philosophical question. So anyway, with that, I'll move on.
And before you do, one of the other members said, here, I also have an unusual visual impairment. So that was a good comment to make.
Well, if those individuals would like to write a short note to me privately at my email address or some other means.
They can contact us at outreach@Halifax. Oh, sorry, observing at Halifax.
Yeah, if they would like to write to me and say a little bit more about their circumstances, that would help me formulate my ideas about this. So I invite those individuals to do so. It might make my proposal a bit more real, if you know what I mean, when I go to the observing committee. Thank you. So what's up this month? Well, the month is almost a third over, but it's been cloudy. So there you go. So I always start with the sun, which is out today. And I checked today's solar activity, which is in the upper right-hand side. That link is active in the online PDF. But when you go there, you will see a big yellow disk with not much going on. It's, we're in solar cycle 25, but there's not a lot going on still. We had a nice big sunspot a few months ago, but not much. So as you see here, we're past the cross quarter day, heading towards the summer solstice, which means the number of hours of night are shrinking. And thanks to daylight stupid time, it gets dark later than ever. So you can see that on the diagrams there. So you have to wait till 10:30 before you can even get going, and then there's not a lot of hours left. So dawn starts pretty early. I've noticed that, and it's going to be earlier yet. The sun's getting higher in the sky, so it is a nice time to be observing, though, because you've got a few hours and it's not as cold as winter time. So if you like galaxies, get out there. And regarding the diagrams I have here for the daylight and night, there is a video of this on the Halifax YouTube channel that you can watch this as an animation. As far as the moon is concerned, it's already past last quarter. Tomorrow is new moon. We missed Saturn north of the moon, Jupiter north of the moon, I think. It's been pretty cloudy the last week. So the new moon is Sunday, and that's in Mi'kma'ki, where we live. That's the birds laying eggs moon. I don't know if any of you are nature lovers, but the birds have been pretty active recently, singing up a storm and making nests. And this is the birds laying eggs moon. In Mi'kmaq, it's Benedemuigus. Again, if you follow that link on the PDF, it'll take you to a little video that we made with Curtis Michael, a Mi'kmaq language teacher. It's a little 30-second thing that teaches you how to say that. Benedemuigus. There's not a whole lot going on with the moon and in terms of conjunctions and that. Mars is going to be very close to the moon on April 17, 0.1 degree north, which makes you think that, wow, yeah. So if you were in Asia, you'd be able to see an occultation of Mars by the moon. So because it's on the other side of the world, we won't be able to see that. But the night before and the night after, Mars will be pretty close to the moon. The first quarter is on the night of the 19th and the 20th. Mark that down because that'd be a good time to do lunar observing. And the full moon comes on the 27th. And because there's a perigee involved, you will have large tides. There were large tides last full moon, and I don't know if anyone noticed, but the perigean full moon tide was a factor in floating that container ship and getting it unstuck from the Suez Canal. The high water of the perigean high tide assisted with that. Just a little aside. So those are the things you missed there. Saturn and the moon and Jupiter and the moon. As far as observing the moon is concerned, you know, I talk about this every month. These are the lunar objects that are in Explore the Universe. So this is these are all of the ones that are in Explore the Universe, and you only have to observe half of each one to do the lunar part. So that's a good start. But if you've done that, or you want a more of a challenge, the next step would to do Explore the Moon. So you should at least try to get out and observe 3 of these, maybe when it's first quarter. But the Moon at Noon program is going on at on Thursdays, well, 1 o'clock our time, for half an hour. And there's a little course there that you can follow. And there's now a workbook you can order, or you can download the materials. We had a really good first session. Actually, we've had 2 now, I think. We had an introductory one, and then we had one which was focused on the first observing day of the cycle. I'm not that involved. I'm kind of in the background helping to answer questions. The hosts are John Reed from our center, Jenna Hines, and I think her name's Sam, Samantha, I can't remember her last name. She's new, but they're all very good. It's a really fun thing to tune into, and they post it right away, so you can go back and look at the old ones. So the planets this month, nothing really much gets going until the end of the month. So Mercury is actually in superior conjunction on April 19, but starting near the end of the month, you'll be able to see it very low in the evening sky. It's going to be hard, but it's pretty bright in twilight. So with binoculars, you might be able to pick it out. And it's headed for its greatest elongation east on the May 17th. That'll be the best apparition for us in the Northern Hemisphere. So of course, it's the greatest elongation east. So you're looking in the western sky after sunset. So try for Mercury. Venus is also moving into the evening sky. It was in superior conjunction March 26th. It is also very low in evening sky starting about April 19th. Difficult, but not as difficult as Mercury. It's pretty bright. Again, use binoculars. And down there at the bottom on April 25th, Venus and Mercury are together. So they fit nicely into a 5-degree binocular view. You should be able to find Venus easily enough. And then with this diagram, you can find Mercury as well. It also might be an interesting photo opportunity for astrophotographers to photograph this conjunction. Mars, it's up there in Gemini. It's a lot dimmer than it used to be. It's going to hang around for a while, but it's really past its observing time. It's got a very small disk, but it's high in the west at the end of twilight, and through the summer will disappear from our view. Jupiter and Saturn are low in the dawn sky. So if you're an early riser and you have a low horizon in the east and southeast, you might be able to do some observing if you're so inclined. Uranus and Neptune, just forget about them. They're just too close to the sun. The one thing we were interested in zodiacal light last month, and we still have a few days here for those that were wanting to observe it or photograph it. There's a few days now before the moon spoils things. If you still want to capture zodiacal light, all you need is a dark and clear sky. Yeah, that's getting pretty rare. As far as Explore the Universe is concerned, Here are the constellations that you need to, that you can observe in the spring, all pretty familiar ones. Ursa Minor, including the Little Dipper, Ursa Major, including the Big Dipper, Boötes, the Herdsman, Leo the Lion is very prominent, Virgo, not so bright, but it's there. Libra, you know, it might be a bit tricky. You have to wait up late, or maybe later in the spring, it'll be easier to see Libra. But those are the spring constellations in Explore the Universe. As far as stars are concerned, these are the principal stars to observe. There's a number of those stars are in the top 50. They're all navigation stars. They're all, well, not all of them, but the ones that are in the top 50, they're all navigation stars. They're SkySafari, SynScan stars, alignment stars, if you have a SynScan type telescope, and the Celestron system also uses those stars other than the ones in Libra for aligning your telescope. So it's good to learn those ones and what their names are, so you find them in the sky, so you know where to point your telescope when you're setting it up, if it's a go-to. The deep sky objects are pretty slim for Explore the Universe, mostly because the spring is really galaxy season, and Explore the Universe is more of a binocular program. So there's not a lot of targets for Explore the Universe in the spring. They're basically star clusters. So the Beehive, the Coma cluster, and one globular cluster. So last month I highlighted the Coma cluster. This month, the challenge is to look for the Beehive. You can even see this from the city. It's a nice little cluster. It looks better, of course, from a dark sky. And to find the Beehive, you look halfway between Castor and Pollux and Regulus, as in that diagram there. That's how you find it. It's in a dark sky, it stands out as a misty patch. In a city sky, you can't see it. But if you just kind of park your binoculars halfway between Castor and Pollux and Regulus, you won't miss it. I put together a double star list, lots of double stars in the spring sky. I'm not going to go through them, but they're all fairly bright and fairly wide. So they're all binocular objects again. That's a nice pastime to pick out those double stars. I'm going to get you started on the double star program as well. So that's it. That's the what's up this month. If there's any questions.
None are in the chat at this point.
Okay.
Thank you very much. And just to recap, if members want to, rather than madly taking notes, you can still refer to Dave's presentation just by going to www.halifax.rasc.ca, and it's on our homepage. You can see his What's Up presentation there.
I see a comment from Bob again. Bob is a pretty sharp guy. He's like keeping me honest here. Bob says, I noticed Vega was not mentioned in the top stars. It's quite apparent in the northeast eastern sky in light polluted eastward viewing from Halifax. You're absolutely right, Bob. However, in Explore the Universe, it's not considered a spring star. That's why it wasn't in my list. I put forward those lists in the What's Up. I mean, I don't tell you everything that you can see. I focus on what's in Explore the Universe for that season. And this is the second month of spring. May will be the last month. When we get to June, I'll swap over to the summer and you'll find it there. So when I made that list of stars, it wasn't the absolute list of stars ranked from bright to dim. It's only the ones that are in Explore the Universe for this season. If you would like to see a more expansive list, go to your Observer's Handbook. I don't know the page number offhand, but in the Observer's Handbook, there is a ranked list of the brightest 50 stars. So anyway, yes, you can see Vega if you, but you know, in ETU, it's a summer star. Okay.
Page 275.
Page 275. There's the editor helping us out there.
Thank you.
Thanks, James.
Okay.
Okay. Thank you very much. The next item up on the agenda is my news from the board. But before we do so, if Adam is still around, which I believe he is, am I correct? I thought I saw him a moment ago. Yes, he's here. There's one question that came in, Adam, if you wouldn't mind answering it, if that's possible.
Yep, I'm here. Sorry. I just had to turn on my video and stuff.
Okay, we'll ask this one question, and then hereafter, if anyone has a question, they'll be answered in person by him via email at a later time. So from Colleen again, if galaxies formed 12 million years ago and all have supermassive black holes, were all galaxies at one time AGNs? If so, how have some galaxies managed to continue making stars to this date and not become like the galaxy you showed us that hasn't had star formation for 10 billion years? Is it just a matter of each galaxy having unique circumstances of formation and growth?
Right. So yeah, sorry, I should have responded in the general chat in case anybody else is interested. I did respond here, but I'll just reiterate my response to Colleen. And so what's going on is that we know that every galaxy has to have a supermassive black hole. But something I didn't mention in my talk was that only about 10% of those supermassive black holes seem to be in like their active phase. So making AGN, right? And so we think that AGN activity is kind of like a phase of galaxy evolution. But essentially what's going on is, she's right, every galaxy has a different set of initial conditions. So some might have more gas or dust to supply to the black hole than others. And those with more will produce a more active black hole for a longer period of time. And those with less will sputter out pretty quickly. And so that plays a role in things. How long the AGN is active will play a role in how much it can govern the star formation of that galaxy. But also, maybe I should have mentioned this in the talk, is that not every AGN has an outflow. So AGN are about 10% of all galaxies, and only about 10% of AGN have outflows. And we don't know why that is. And that's something that I'm trying to work on over the course of my PhD, is figuring out, comparing galaxies with outflows and those without, and trying to examine and explore any differences between them. And at this point in time, it is not very clear where those differences are. So for example, some of the galaxies with very large radio jets, and compare them to those without any of those jets, they don't look that different from the perspective that I use, which is at X-ray wavelengths. They look pretty similar across the board, which is really strange, because you figure there'd probably be something different about them somewhere. But at this point, this is preliminary results so far. It doesn't look like they're that different. Now, those with winds, it appears as though those objects that have a lot of material being funneled onto the black holes are most effective at producing winds. And if you think about it, that kind of makes sense, because the explanation for how a wind is produced is through the high radiation being capable of pressing material out of the black hole region instead of onto it. And so it seems to be a weird self-regulation mechanism where if you have a bunch of material flowing towards your black hole, you suddenly make a really bright central engine, but now that brightness is pushing your material away in a wind. So you're not feeding very effectively anymore. So kind of to answer the question, we're working on it. We're trying to work on things.
So we can expect you as a guest in a year or two?
Sure, yeah, for sure. I can come back, absolutely.
Wonderful. Just let us know when you're done and we'll invite you.
All right, awesome, thank you.
Great, wonderful. Thanks so much, Adam.
No problem.
Okay. So the last presentation before we say farewell to everyone is the news from the board, which is this one. Halifax Center, we can be reached on our website at halifax.rasc.ca. And if you, those questions that I mentioned to members, if they want to send them, or if you have any inquiries at all, you can send them to me through the email, general email at president@halifax.rasc.ca, and I will answer them or forward them to those that can. One of the things that we did at our board meeting on April 6th was reviewed and approved the guidelines regarding SCO use. I want to thank David Hoskin and Kathy Walker for their work in reviewing the guidelines and providing the changes to it. The parts that you see in blue font are the parts that have changed, and I'll try and provide some explanatory notes here as to why they changed. For instance, there's still only 10 people allowed on site. That has not changed through the provincial guidelines. But what we have done is clarified and altered some of the numbers. So we can now, there used to be only two people on the roll-off. We now allow up to 4 additional. There can be, and the part about 3 people, 1 per concrete pad is still there. And the remaining 3 individuals, if you add 3 plus 4 is 7. So the additional 3 can be anywhere else exterior to those locations, as long as they maintain 2 meter distancing. Keeping in mind that if there was a family unit, same household or a bubble, that bubble does not count as 1 person. If there are 3 people in that bubble, that's 3 people of the 10. Okay, so I got to keep that in mind for that. So that is where that has changed. How we announce who's going has not changed, but if 10 people have already expressed their intention to go, do not go. And we politely ask that you police yourselves in this regard. In other words, when you are planning to go and you announce through the announce list, keep tabs on how many people have already said they are going, so that once the 10 has come up, that's it. But please, if you are not going to go that night, also let the announce list or the discussion list know, so that perhaps someone who is considering but now knows there are 10 knows that there's 1 spot now, so they can take it. And if you arrive at SCO and find 10 people already there, we would truly appreciate it if you leave and go elsewhere. We would hate for our ability to have anything at SCO come to a cease and desist situation because we did not follow guidelines, provincial guidelines. The warm room and roll off, just for clarification, no more than 3 people, that used to be 2, in the warm room with masks. Masks must be worn. And no more than 4 people in the roll off, again with masks. Recognizing that at certain points of the year, if lens fogging is a problem, masks may be temporarily removed from the nose for the duration of the task, provided no one is within 2 meters of you. One of the other solutions that you can do is put tape of some sort at the top of the mask underneath your glasses, so that the steam from your breathing won't go up into your glass. Just something to consider. And at this time, vaccination is not a factor, since there's not evidence yet that vaccinated individuals are not able to contract and spread COVID or any of its variants, even though they may not exhibit any clinical signs of the infection. And again, we politely ask that members police themselves. If someone is not wearing a mask, please politely ask that they do wear one. And a few masks will be available for the use of those who forgot to bring one. They will be on site in the warm room, although members are strongly encouraged to bring their own. That is part of the guidelines, is that you have that prep kit ready to go, including your mask. The 2 meter physical distancing has not changed. Non-use of the third binoculars has not changed, but you still can use the 16-inch Dob on site, provided you bring your own eyepieces and clean the surfaces prior to and after use. You must bring your own sanitizing equipment to clean all the common surfaces that you touch with your hands, especially if you are the last person there. The doorknobs, the keypads, the locks, tables and counters, chair backs, light switches, toilet paper container. And yes, there is toilet paper in an ice cream container in the storeroom slash toilet. The toilet seat and the toilet crank. And if you are using keep note that the hand sanitizers must contain the 60% alcohol to be effective. That was required. And in the recommended part of the policy, there is a descriptor about preparing a SCO sanitization kit with all the necessary items, suggesting that you make it ahead of time and have it ready to go when you pack all your equipment. And your kit should include that hand sanitizer, a sanitizer, a face mask, gloves, and paper towels. And if you are preparing a bleaching disinfecting solution because your sanitizer isn't at least 60% alcohol, then it should be made the same day in order for it to be effective. And the other pieces with respect to cleaning all the surfaces, practicing good hygiene, and if you're unwell, please don't go to SCO. And certainly garbage in, garbage out. Provide your own garbage bag for everything that you use that is now considered to be garbage. And that is in effect immediately, all of this. Good news, John Reed, our own member, has completed the Explore the Moon telescope. Congratulations, John. I know that Dave mentioned that John had completed it. He's quite excited. He used the new reference materials that you see here. The blue book of Explore the Moon is for small telescope use, and the red one is for those of you that want to view it with binoculars. And keeping in mind, there is a difference in the number of items to observe with the two programs. And as Dave mentioned, RASC does have the moon at noon. It's called the moon at noon because it's noon in Ontario where this is hosted, but certainly go onto the RASC website and you can register for it. Currently, each of the two sessions so far, we've had 8 of our own members attending it, and it's a great thing to view. Even if you don't plan on completing the program, it's still interesting to learn a bit more about the moon and everything related to it. As always, I'd like to announce about our Halifax Center stars. On the RASC Weekly and the masthead for the week of March 24 to April 4. Congratulations, David Hoskin, for the astro image of the week of his photo of the spiral galaxy M81. And the RASC Weekly has gotten into the habit of featuring those photos from members who have completed the astro image certificate. And it's now official. It was announced in the RASC Bulletin on April 1st, and it's no joke. The Blair McDonald has received his service award, and you can see the photo there of his medal. James Edgar, congratulations. He will be receiving a wall plaque and certificate that so far he hasn't received, but I'm sure we'll be getting very shortly. And speaking of James, he's also in the Journal of the RASC in the April edition. The inside cover contains the photo you see on the left of the moon. And I'm saying April Fools because in the descriptor for that particular photo, he says, Samaj Raj from the Tower of the Bastille in the July 1989 uprising using an eyepiece projection. Well, I think you can appreciate that that really isn't what happened. He describes above what I've written above the photo there is how he took that photo. And James is into woodworking, and I don't know what a CNC carving machine is, but it's quite impressive. And that was a piece that he put onto African coral wood that he has carved using this particular carving machine. So it's quite impressive. And that's on the inside cover under Great Images by James Edgar. So thanks, James, for both of those. And thank you for the double image as well. Also, just a reminder regarding Nova Notes, if you haven't already, the volume 52, number 1 is on our website for your viewing pleasure. Excuse me. The March-April edition will be coming out later this month. If you have anything that you would like to submit, photos, sketches, an article that you're considering, please let the editors know by April 18. And if you just email it to novanoteseditor@halifax.rasc.ca, they will get it. Both of them will get it. And if you forgot what the email address is, just go to our website and About Us, and the email address is there. So I mentioned with all the perks that you get, the handbook and all the other stuff that you get by joining RASC, this is how you join. First of all, you go into our website in the section About Us, and you see this particular column on it. So you can join Halifax Center online. If you click on the word join, it will bring you to the National RASC site where you can type in all your wonderful information, and join online. And be sure to have Halifax Center as your center of choice. Or if you're old school and prefer to fill out a form in paper and send in a check, just click on form and you can do that as well. Excuse me. Recognizing that the pandemic has created some financial challenges to some of our members or prospective members. If you need assistance, contact Adela Ziffi through National RASC at mempub@rasc.ca and explain the situation, and she will see if she can help you in any way. We mentioned the other perks, and these were national perks, the Halifax Center perks. You can have the email discussion group. By clicking there, it'll take you to the page at which you can join that discussion group and participate in it. And also there's a link to our St. Croix Observatory site so you can see information about St. Croix Observatory. Our upcoming meeting dates, our next one is May 1st, and it will be a webinar versus our meeting format that we have been using for several months. And we're quite thrilled to welcome Chris Gaynor, who's from RASC Victoria Center, and he'll be addressing amateur use of the Hubble Space Telescope. So that's quite exciting. And Tony Schellink will give us the basics of lunar sketching. Those of us that saw Michael Gatto with his presentation on Mars, Tony will give us some basics on how to sketch. So that'll be quite exciting to watch as well. You can see all the other dates that are there, and we are working on October 2nd and November 6th. We've got some surprises there, so we'll wait to keep you apprised of that. And nationally, the GA is being held June 25 to 28. It will be virtual again this year, but stay tuned either on the national site, and they certainly will announce things as they become known through the usual means, email, etc., and on their website. So, any questions? There's a question here about, could you provide some guidance to those of us who would like to use SCO but need to be checked out before gaining access privileges? Thank you. First of all, to have access to SCO, I believe our guidelines do require you're a member for at least 1 year. And then basically, once that happens, should be in touch with John Ledard, who is our SCO manager, and he will be able to either he himself or he will arrange for someone else to go out to SCO with you and give you the what's what of the center. And you'll have to request a key if you wish to do so. Hope that answers the question.
Judy,
Yes.
you kind of glossed over when you were talking about contacting Adela Ziffi at the national office.
Yes.
About, there is an emergency fund set up for people who, for one reason or another, because of the COVID pandemic, can't pay their dues. There's an emergency fund, and it's somewhere in the neighborhood of $100,000. So if you can't pay your dues, then contact Adela, and she will arrange to have them paid for you.
Okay. Thanks for that clarification, James. Anything further? Okay. Well, thank you everyone from near and far, from coast to coast, for attending. Yes, Dave, $100,000. Wow, is right. But anyway, this brings us to the end of the formal part of our meeting. And in just a second, I will turn off all the recording, and everyone is welcome to join us for the Astro Chat portion, which is very informal and can ask questions and just generally chat and say, hi, how you been? So thank you everyone for attending, and thanks to our special speakers, to Adam, Dave, and Melody, thank you so much. And to the three individuals who presented their questions and to the people who answered them, another thank you. So take care, everyone, and we will see you again on May 1.